Welcome back. So we spent the last few classes looking at how images can be formed by mirrors. The images are formed because of reflection. However, next we want to look at the formation of images using lenses. In order to understand how images form from lenses, we need to be able to use the law of refraction. So refraction, or the bending of light, occurs because light travels at different speeds in different materials. That means that when light travels through an interface between two materials, it may cause the ray of light to bend, and this bending of the direction of light that occurs at an interface is called refraction. We see in our example here that light is bouncing off of a pencil and heading towards our eye. When the light goes from air to glass, the light bends, and when the light travels from water to glass, the light bends a different amount, so it looks like the pencil is distorted. The reason for this is that the speed of light in water is different from the speed of light in glass, and it's also different from the speed of light in air. So the speed of light is smaller in water than in air, and it is even smaller in glass than both air and water. In order to keep track of the change in speed, we will use the index of refraction, n. The index of refraction is the speed of light in a vacuum divided by the speed of light in that material. So the speed of light in a vacuum is 3 times 10 to the 8 meters per second, and the speed of light in air is effectively the same, 3 times 10 to the 8. So the index of refraction is 3 times 10 to the 8 divided by 3 times 10 to the 8, which is equal to 1. The speed of light in air is very slightly slower than it is in a vacuum, but it's close enough for this class that we'll just call it 1. Notice the index of refraction is unitless. It is meters per second divided by meters per second, so the units all cancel out. If we take water, the speed of light in water is about 2.25 times 10 to the 8 meters per second, so light is slower. So to find the index of refraction, we divide the speed of light in a vacuum, 3 times 10 to the 8, by a 2.25 times 10 to the 8, the speed of light in water, and we get an index of refraction of about 1.33. So the index of refraction is always greater than 1. That's because nothing can go faster than the speed of light in a vacuum. Okay, so how does changing the speed of light cause light to bend as it goes through an interface? So to think about this, we will use an analogy of when a car or a truck drives from a road into mud. The point is that the car's wheels make good contact with the ground on the road, but in the mud, the tires slip and the speed is decreased. This is just like how the speed of light is decreased when the light moves from the low to high index of refraction material. So in our analogy, if a car drives straight into the mud, the car just slows down. However, if the car drives into the mud at an angle, something interesting happens. So if our car is driving into the mud and the right wheel hits the mud first, then the right wheel will slow down. But the left wheel is still on the road, so the left wheel is going to keep going at the same speed. When the two wheels are traveling at different speeds, then the car will turn. So in this analogy, the right wheel slows down, the left wheel pushes ahead, so the car is going to turn to the right. The same thing happens in light. In our picture here, we have two materials, material 1 with a smaller index of refraction, and material 2 with a larger index of refraction. The blue line is the incident light, so as it travels through the low index of refraction, the high speed of light material, it goes in a straight line, but when it hits the material, the right-hand side of the ray hits the mud, or the higher index of refraction material, and it slows down. And the left-hand side moves faster for a very split second, so it causes it to turn to the right. This means that we are going from a low to high index of refraction. The angle of incidence decreases. If we went the other way, say the red line was our incident ray, then the right-hand side would hit the high-speed material first, so the angle of incidence would increase. The formula for this is called Snell's law, and it is n1, the index of refraction of material 1, times the sine of theta 1, and that is equal to n2 times the sine theta 2. The angles are the angle of incidence, so the angle between the normal line that is perpendicular to the surface, so an angle of 0 would be one that's exactly perpendicular to the surface. Snell's law tells us that if we know the indexes of refraction of the two materials and one of the angles, then we can find the second angle. Further, if the index of refraction is larger than the sine then the sine of theta must become smaller, so theta must be smaller. That means for the larger index of refraction material, the angle theta will be smaller, and for the smaller index of refraction material, the angle will be larger. Okay, let's do an example. We have a ray of light that moves from air to glass with an incident angle of 30 degrees. The index of refraction of air is 1, and the index of refraction of glass is 1.6. We would like to find the angle of refraction. Okay, so we're going from air to glass, so low to high index of refraction, and that means we expect the angle to decrease. So we take Snell's law and isolate the sine of theta 2, and we get that the sine of theta 2 is equal to n1 divided by n2 times the sine of theta 1, and we plug in our numbers and get 1 over 1.6 times 0.5, which is the sine of 30, and that gives us 0.3125. Now we use the inverse of sine to get the angle. This is a lot like the inverse tangent we did in 201 and on the first homework. Anyhow, so we do the inverse sine of 0.3125, and that is equal to 18.2 degrees, so that's the angle of refraction. Notice the angle did get smaller as we expected when we went from a low index of refraction to a high index of refraction. Okay, I want to talk a little bit about total internal reflection. So when light travels from a high index of refraction material to a lower index of refraction material, the angle will increase. So as the angles in the glass, so our light here is traveling through the glass, as that angle gets larger, eventually the refracted angle becomes 90 degrees. That means that the refracted angle is too large for the light to actually leave the material. So when this happens, all of the light is reflected. This phenomenon is called total internal reflection, and this is used in fiber optics cables where light travels through the cable and the incident angle is large enough from the normal that that means all of the light reflects. So you can send light incredibly long distances because all of the light is reflected. Okay, you have a couple questions to do, so good luck with that.